Hello students, welcome to experiencetutor.com and YouTube channel Experience Tutor. Today we'll discuss class 10th mathematics real number part 4. And here is our welcome message. Before we begin the lesson, please request you to subscribe, like and share this video. Please click on the subscribe button to support us and click on the bell icon so that you can get regular updates whenever a new video is uploaded. Let us begin the lesson. Today we'll first start with a theorem. The theorem is, let P be a prime number. If P divides A square, then P divides A, where A is a positive integer. So we are telling that for any prime number, if it divides A square, it is also divided by A, where A is a positive integer. Now proof. Let the prime factorization of A be as follow. Just we have considered that P1, P2, Pn are the prime factorization of A, where P1, P2, Pm are primes, not necessarily distinct. Therefore, squaring both the sides, we get A square is equal to under bracket P1, P2, Pn bracket close, again second bracket open, P1, P2, Pn bracket closed is equal to, if we multiply both the thing, then we'll get P1 square plus P1 square, P2 square, Pn square. Now we are given that P divides A square. Therefore, from the fundamental theorem of arithmetic, it follows that P is one of the prime factors of A square. However, using the uniqueness part of the fundamental theorem of arithmetic, we realize that the only prime factors of A square are P1, P2, Pn. So P is one of P1, P2, Pn. It may be P1, it may be P2, or it may be any other factors, or it may be Pn. Now since A is equal to P1, P2, Pn, P divides A. Hence it is proved. Now let us see the next theorem. Next theorem we have to prove under root 2 is irrational. So proof is, let us assume to the contrary that root 2 is a rational. So we can find integers r and s is not equal to 0, such that root 2 is equal to r upon s. Suppose, since it is, we have considered that it is rational, so we can write root 2 is equal to r upon s. Suppose r and s have a common factor other than 1. Then we divide by the common factor to get 2 root 2 is equal to a upon b, where a and b are co-prime. So we can write b root 2 is equal to a by cross multiplying. Squaring both the sides, we get 2b square is equal to a square. Therefore 2 divides a square. It is simple. 2 divides a square. Now 2 divides a also. By the theorem, if prime number is divided by a square, then it divides by a also. So we can write a is equal to 2c for some integer c. Substituting for a, we get 2b square is equal to 4c square. That is, b square is equal to 2c square. This means that 2 divides b square, and so 2 divides b. By theorem, if a prime number divides by a square, then it divides by a also. Therefore, a and b have at least 2 as common factor. But this contradicts the fact that a and b have no common factors other than 1. This contradiction has a reason because of our incorrect assumption that root 2 is rational. So we concluded that root 2 is irrational. Our next problem is prove that root 3 is irrational. So let us assume to the contrary that root 3 is rational. That is, we can find integers a and b not equal to 0 such that root 3 is equal to a upon b. Suppose so till now we have seen, let us assume we have to prove that root 3 is irrational, so we have assumed that, let us assume to the contrary that root 3 is rational, and that is, we can find integers a and b which is not equal to 0 such that root 3 is equal to a upon b. Suppose a and b have a common factor other than 1, then we can divide by common factor and assume that a and b are co-prime. So b root 3 is equal to a. Squaring both the sides, 3b square is equal to a square. Therefore, a square is divisible by 3. And it is also divisible by a by the below theorem. Theorem says that if a square is divisible by a prime number, then a is divisible by the same prime number. So we can write a is equal to 3c for some integers c. Substituting for a, we get 3b square is equal to 9c square. That is, b square is equal to 3c square. This means that b square is divisible by 3, and so b is also divisible by 3. Theorem: if a square is divisible by any prime number, then a is divisible by the same prime number. Therefore, a and b have at least 3 as a common factor. But this contradicts the fact that a and b are co-prime. This contradiction has arisen because we have incorrect assumption that under root 3 is rational. So we conclude that root 3 is irrational. Our next problem is so that 5 minus root 3 is irrational. So solution is, let us assume 5 minus root 3 is rational. That is, we can find co-prime a and b which are not equal to 0 such that five minus root 3 is equal to a upon b. Therefore, we can write 5 minus a upon b is equal to root 3. Square rearranging this equation, we get root 3 is equal to 5 minus a upon b is equal to 5b minus a upon 5 upon b. Now, since a and b since a and b Since a and b are integers, we get 5 minus a upon b is rational. And so root 3 is rational. But this contradicts the fact that root 3 is irrational. This contradiction has arisen because of our incorrect assumption that 5 minus root 3 is rational. So we concluded that 5 minus root 3 is irrational. Our next problem is show that root 3 by 2 3 into 3 root 2 is irrational. Solution: let us assume to the contrary that 3 root 2 is rational. That is, we can find coprime. A and B not equal to 0 such that root 3 by 2, sorry, 3 root 2 is equal to A upon B. Rearranging we get root 2 is equal to A upon 3B. Now since 3 since 3 A and B are integers, since 3 and B are integers, A upon B, 3B is rational. And so root 2 is rational. But this contradicts the fact that root 2 is irrational. So we concluded root 3 root 2 is irrational. So it is proved. And this is the end of today's topic. Please subscribe, like and share our channel. Please click on the subscribe button so that you can get a notification whenever a new video is uploaded. Please click on the bell icon. Thank you for watching our video. Keep watching.